I'm going to talk something about a new class of models that we are proposing for modeling infectious disease models. We call it as a geographically dependent individual level models. So here is my outline. First of all, I will give you a brief introduction of individual level models. Then we are going to propose a new class of models, geographically dependent individual level models. Then I will talk about two versions of these proposed models. One is in discrete time, another one is in continuous time. And I will show you the examples in both simulation and real data for discrete time geographically dependent individual level models and for
Sorry,
continuous
Maxine,
time for
sorry,
simulation
Maxine,
study.
sorry, Maxine, to interrupt you. Can you make it like a full screen, please?
Sorry?
Can you make it a full screen? Your.
Yeah, is it now better?
The like a right hand side is a little bit, I don't know. Can you make it like a
This one, right?
Yeah.
Okay. Yeah, for sure.
Okay.
Thanks. So first of all, I would like to give you a brief introduction. As you know, infectious disease models are important for understanding the underlying disease mechanisms that influence the spread of disease and predicting future disease progression. And it caused by, pathogenetic microorganisms such as bacteria, viruses, and parasites. So the model I am going to talk about, it is like mechanistic models, and it takes into account individual levels information on individual units. It can also accommodate heterogeneities in different ways and different risk factors as well. So in recent years, there has been rapid progress in developing spatio-temporal models of infectious diseases, and with particular interest in the development of statistical methods to fit such models to diseases and with data. So one recent examples and developments in this field is called discrete time individual level models. That can be used to make inference about the spread of a disease through a heterogeneous population. And the important feature of this ILM, we call it ILM, is that it can take into account like covariate information on both susceptible and infectious individuals, as well as their shared covariate information. And such kind of ILMs can be used to identify possible risk factors, predicting the course of an ongoing outbreak, or evaluate control measures. So the general form of the ILMs is defined as like this one. We call it PIT is the probability of a susceptible individual I being infected at time t. And it looks like this form where omega s is the susceptibility function and omega t is the transmissibility risk functions. And this is called the kernel function, and the epsilon term is called it as a Sparks term.
So Maxine, sorry to interrupt you. It seems that we are still in the title page of your presentation. I don't know. It doesn't move. Can you check it from your side?
Yeah, sure.
Because we are still in the a title page.
Can you see it now? No.
No, it's still we are in the a title page.
Okay, then I have to maybe share it again.
Yeah, do it please.
Yeah, sure.
Yeah, it is good now.
Now it works?
Yes.
Oh, thank you. Thank you, Mahmoud.
You're welcome.
So as I said here, PIT, I call it as a probability of a susceptible individual I being infected at time t. And omega s is the susceptibility function and omega t is the transmissibility function, and kappa, this one is the, we call it as a kernel function. And the last term is the epsilon term is a Sparks term. And IT is called the set of infectious individuals at time t. And if we make a particular case, for instance, omega s equal to 1, and omega t, the transmissibility function is just constant, or vice versa.
Mahsin,
Yes.
sorry again to interrupt you. Can you make it to the full screen? Okay, it seems that we can see, but not the, all of the, but the, like a page size, like a number, we don't see it. Can you make it like a to full screen?
Yeah, for sure. So I don't know what happens. Yeah, I'm going to do it again, maybe.
Yeah, please. Sorry to interrupt you.
No, it's, I opened it before, that's why maybe.
So the line said whether you may want to, share your full desktop rather than your screen. I don't know that. Sarah, can you jump in to say that I don't know?
I've had this happen in other settings in Zoom.
Okay.
If you stay out of the full screen mode, you can usually forward your so it seems to go to pause share when you go to full screen. So if you don't go to full screen, you might be able to advance the slides and we can see. So don't do that.
No,
Oh wait, there it goes.
Now it works?
Well, it's blank now. It changed.
So it's blank now.
Oh my goodness.
Now we're on the outline. Yeah, don't go to full screen, just advance. That works, I think. You can close the window on the right with that sidebar, and that'll fill up most of your screen.
Yeah, this is what
There you go.
I think that is good now. Yeah, that is perfect. Thank you.
Now,
Thank you, Lance. Thank you, Mahsin. Yeah, go ahead, please.
No, not going to the full screen, just using this one?
Yes,
you're
that's
good
correct.
now.
Yeah,
you're good now.
Yep.
Oh, thanks. It works?
Perfect.
I apologize, for it, for technical issues. So as I said, I just gave you an overview of the individual level models, how we define it. And the spatial case of the individual level models, I define it in the terms of rate of infectivity of susceptible individual I. It's going to like this term, where we could take different types of transmission kernels, such as exponential kernel, Gaussian kernel, power law, or Cauchy type of kernel. And these spatial ILMs are well developed and provide a common framework for modeling many disease systems. They currently assume the probability of disease transmission between two individuals depends only on their spatial separation or distance and not on their exact spatial location. So in cases where spatial location itself is important for understanding the spread of emerging infectious diseases like COVID, and identifying their causes, it would be beneficial to incorporate the effect of a spatial location in the model. So we thus generalize the ILMs to a new class of models defined as geographically dependent individual level models. And it takes into account the evaluation of the effect of spatially varying risk factors as well as unobserved spatial structure upon the transmission of diseases. So more specifically, we consider a conditionally autoregressive model to capture the effects of unobserved spatially structured latent covariates or measurement error. So this results in flexible infectious disease models that can be used for formulating like etiological hypotheses and identifying the geographical areas of unusually high risk to formulate preventive action. So we define our geographically dependent individual level models or GD-ILMs like this way. So it takes in the same way in the same way of ILMs, but the exception is here we stratified the area into k different areas. So here k represents the area index from I to k. Another exception is here in the set of infectious individuals in the ILMs. We consider the number of infected individuals at time t in the whole study area, but it is computationally too expensive. So in our GD-ILMs, we consider the number of infected individuals at time t in area k and their neighboring areas. So we define the neighboring areas for area k as A, the other areas who shared common boundary. So in particular, if we take a special case, for instance, transmissibility function is set to 1 and the susceptibility function, which takes into account different types of risk factors. So first one, with the vector of alpha 1 parameters, we take into account the risk factors for the individual units in area within area K. The second risk factors with regard to the parameter vectors alpha 2 is area level covariates. For instance, environmental variables like temperature, humidity, and other environmental covariates. For the third set of covariates, which takes into account the environmental variables. So second one is for area specific, first one individual within area, and third one is environmental variables. And the epsilon k is the spatial random effects parameter. So we consider the traditional conditional autoregressive model for the spatial random effects. So for instance, if we take the kernel function as a power law kernel, then we could define the rate of infectivity for the ith susceptible in area K at time t would be like this one. And this is for discrete, using discrete time. So as I said, for spatial random effects, we consider different types of conditional autoregressive model. There are a number of CAR models that are widely used in disease mapping. For example, ICAR, PCAR, LCAR, and convolution model. In this study, we consider LCAR model. And you know, the LCAR takes, like this form. And for fitting the GD-ILMs, we takes into account like Bayesian framework with MCMC iteration, and the likelihood function takes this form. Now I would like to explore the simulation study and the application of our proposed GD-ILMs for the real data. So for simulation purposes, we consider two different types of models. One, we call it as a region restricted. The other one, we call it as a global model. So the region restricted, we call it because we consider for the number of infected individuals at time t in area K and the neighboring areas. So this is for the simulation model. And the second one for simulation model is global model. We take all the infected individuals in the whole study area at time t. But for fitting purposes, we consider only the region restricted model for all different, settings for two different types of models. In addition, for simulation study, we consider three different scenarios. Scenario one, we simulate epidemics from the region restricted model, that is model one, based on 9 dissemination areas as infected initially, and it is based on real data. So I would like to say more specifically where I explored the simulation study, which area. So for simulation study, we consider the city of Calgary in the Alberta province in Canada, and the city of Calgary has 16 different health areas. They call it as a local geographic areas. And to simulate the realizations of an epidemic, we consider these two different models for the 16 local geographic areas. And within the local geographic areas, we consider the individual units as a dissemination area. So dissemination area is the smallest spatial unit in Canada, and and the average population for a dissemination area is between 400 to 700. And in Calgary, there are about 1,570 dissemination areas, so that we treat our individual units within a local geographic areas. So that is the scenario one. And scenario two, we simulate epidemics from the global model that we defined this one, model two. And we start with 9 infected individuals. And how we start the 9 infected DS, it's based on the real data that we got from the Alberta Health, a Ministry of Health in the Alberta government. And the third scenario, we just start with a random initial infection or infected DA at the start of the simulation. So these are three different scenarios we considered for our simulation studies. In addition, we consider two different settings, three different settings based on the spatial correlation for the LCAR model. One is, we call it as a strong correlation. We set the spatial autocorrelation parameter as a 0.08. The second one, we call it as a moderate, and the spatial autocorrelation parameter is set 0.05. The third settings we consider as a weak spatial autocorrelation, and the spatial autocorrelation parameter is set 0.3. So there are three different settings and three different scenarios for the simulation study we considered for our GD-ILMs for using discrete time. So this is the simulation study for scenario 1, how the disease is spread over time, just the exploratory analysis. And for another thing I would like to mention for simulation study, we consider SIR, compartmental framework, and we assume the average infectious period is 3 days or 3 time units, and it is assumed fixed for all the individual units. So that's why you see here a subset of realization of the epidemic in the first 9 time periods. The gray time periods is the susceptible units, and the red points represents uh, newly infected individual units, and the blue dots represents the removable units over time. So this is the simulation subset of the epidemic progress map. Again, exploratory analysis for second scenarios, and this is for third scenarios. So third scenario means we start with one initial randomly infected DA, and you see how the disease is, spread out over time. So based on our simulated data, we fitted the models in Bayesian framework via an MCMC algorithm. And for fitting purposes, again, we always use the region restricted model. And you see, this is the scenario for strong spatial dependency. And in the x-axis, there are S1, S2, and S3 represents 3 different scenarios. And the fixed effects parameter alpha is intercept, and alpha 1 is the covariate parameter. For simulation purposes, we consider the population size for each DA as a covariate, and that is the only covariate we used. And delta we consider as a spatial autocorrelation parameter. Sorry, delta here we consider a spatial dispersion parameter in the kernel function, and we used the true parameter set to 4. Here again, the rate horizontal line represents the true parameter set that we used for simulation study. And these results represents the posterior means and 95% quantile based credible intervals for each model parameter and for each simulated epidemic in case of strong spatial dependency. So we consider 10 different simulated epidemics for each different scenario and each different settings. So the only thing you noticed here for the spatial dependency parameter, for scenario 2 and for scenario 3, it is underestimated. Because one thing, for data simulation and data fitting, there is a mismatch between S2 and S3 scenarios. For data simulation, we used global model, but for data fitting purposes, we used region restricted model for S2 and S3. So there is a mismatch. So only thing we found underestimated the spatial dispersion parameter. But for other parameters, the estimated posterior means and 95% credible intervals all, overlap the true values. So this is for second settings. Second settings means considering moderate spatial dependency, and we have the similar conclusion. So only spatial dispersion parameter is underestimated in second scenario and third scenario. This is for weak spatial dependency setting, and we have similar conclusion. So, and this figure represents a subset of the random effects parameter for six spatial random effects parameter for all different scenarios, 3 different scenarios. So here you see the posterior mean and 95% credible interval. It truly captured the true value for all different scenarios for the spatial random effects. So this is the simulation study. Then we applied our proposed GD-ILMs for real data. So we got the seasonal influenza outbreak data from the Alberta Health, Ministry of Alberta government. And for the seasonal influenza outbreak data, we consider 2 different compartmental frameworks. One is SI, susceptible infected, and another one is SIR model. So here is the real scenario for the Alberta or Calgary influenza outbreak data for the first 9 days. You see in the October 25th, there are 9, individual DA is infected that we consider as the initial set of infected DS in our simulation study. And over time, again, the red dots represents the newly infected DS, gray dots represent susceptible DS, and the blue dot represents the DS which is removed over time. So based on our GD-ILMs and fitting to different compartmental frameworks, the the posterior mean and 95% credible intervals for the fixed effects parameter are represented here. So delta represents the spatial dispersion parameter. You see here the spatial dispersion parameter posterior mean is very small. So it means that we didn't get, a spatial signal for transmission of influenza for the city of Calgary. And alpha 1 represents the population covariate parameter. So that means population size for each DA. And here we found that under both frameworks, the population size has a positive effect on influenza transmission. So with highly populated DS are more likely to promote the spread of influenza to other DS. So finally, in order to make the results of inference more directly relevant to the development of disease surveillance and control, we construct posterior distribution of infectivity rates that quantify the LZA level infection risk over time. The posterior mean infectivity rate for each susceptible individual DA was determined based on the posterior mean of the fixed and spatial random effects parameters. And then it was summarized by averaging over the susceptible DS as function of time. So the average of the posterior infectivity rates can be used to produce risk maps like this one for showing the spatial distribution of LZL level or 16 health region level infection risk at a given point in time. So these maps may be used to inform targeted surveillance by ranking the LZS in order of the most likely to be infected. So this is a subset of the risk maps for influenza outbreaks during the period of October 26 to November 6, 2009, and across the 16 health regions for the city of Calgary. So this is the, application for GD-ILMs for discrete time. So now I would like to talk about the continuous version of our proposed GD-ILMs. So we define the rate of infectivity in the similar way that we define for discrete time for GD-ILMs, but the exception is here we consider T as a continuous time or real time, and the likelihood function is different than the discrete time GD-ILMs in the continuous time. And we performed the simulation study for the continuous time GD-ILMs. So for simulation setup, again, we consider three different settings: a strong spatial dependency, moderate spatial dependency, and weak spatial dependency. Also, we consider two different scenarios, not three different scenarios like discrete time. So scenario one is considering the region restricted model S1 that is represented on the x-axis level, and scenario two is labeled as S2, that is for global model. So again, for simulation purposes, we consider both of these models, but for fitting the GD-ILMs for continuous time, we consider only region restricted GD-ILMs. So here on the right hand bar, you see different, parameters. Again, alpha is intercept, and alpha is the population size for is DA, covariate parameter. Here we define beta as a spatial dispersion parameter. We have different notation in discrete time. We define it as a delta. And lambda E here is also a spatial dependency parameter. And sigma is the LCAR, overall standard deviation parameter. And here, delta represents different things. In our discrete time GD-ILMs, we consider fixed infectious period for all the individual units. But here we assume like gamma distribution to generate the infectious period for the SIR model, and then we estimate the infectious period rate. So the infectious period rate is defined as the delta parameter here. And another additional things we consider in our continuous time is a Sparks term. We set Sparks term equal to 0 in our discrete time model. But here Sparks term represents the infectious pressure coming outside from other sources. So these are all fixed parameters. In addition, in our continuous time, we consider time of infection as unknown, but in our discrete time, we consider as a known. So here in continuous time, we consider data augmented MCMC for the latent, parameters. And based on that, we again use random walk Metropolis Hastings algorithm for the MCMC iterations. So these are the simulation for three different scenarios. Again, we find the similar conclusion that we found in our discrete time. So here beta, you see the spatial dispersion parameter again underestimate for the continuous time. It was also true for the discrete time because there is a mismatch between data generation and data feeding models. And this is the first 6 sets of spatial random effects for 3 different settings and 2 different scenarios for continuous time. And again, the spatial random effects parameter For the true value, it falls between in the 95% credible interval. And we are applying our continuous time GD-ILMs to the same to the same real data, and we are also planning to apply the GD-ILMs continuous time for the COVID data in the city of Calgary. In conclusion, GD-ILMs enables inference to be made about infectious disease dynamics with respect to time and space, while accounting for unobserved spatially structured latent covariates or measurement error. And we shown that new GD-ILMs can be used to conduct risk assessment via posterior infectivity rate maps that account for a spatial structure. And the modeling framework can be extended to allow more complicated disease systems like SI, SIR, or SINR, or SEIR, so different compartmental frameworks. And data augmentation techniques we used for infection and removal times as latent variables for SINR scenarios for unobserved quantities. So another thing is the cons is the fitting those kind of individual level models is computationally expensive, and it is also true for GD-ILMs as well, if the number of individual units is going to increase. So in our future work, we will work on more computationally efficient methods such as approximate Bayesian computation or Gaussian emulation process for GD-ILMs to carry out statistical inference on infectious disease dynamic systems. So thank you all, and these are all references.